Okay. Yesterday we're talking about it. A very important, please. Very important. What is exactly the QPSK? I mentioned it. Okay. QPSK, absolute. Just I'm going to repeat for 5 to 10 minutes because let me start up the M array. Okay, exactly. Yeah. Look back here. The quadrat space. Exactly. This is QPSK is the one. Please remember the BPSK. The binary PSK is the one. Whatever the transmitting the message, the symbol that is binary symbol 190, we change the phases of the carrier wave in one carrier wave itself. For example, the phases of the carrier wave for a transmitting one will be changed as soon as the carrier, changed. If any, as soon as the one comes, another phase will be of the same carrier wave will absolutely get changed. Where exactly in QPSK, what will happen? Let us say we want to transmit the one. Let me say one. Then it means a symbol one. What will happen? We're going to send it two signals. S1 of t and S2 of t. S1 of t with a phase, let me say cos omega ct. S2 of t will be different phase of the S1 of t. If S1 of t is a cos omega ct, S2 of t will be sin omega ct. Okay, exactly. Sin omega ct, which is absolutely mentioned. Look back here. In this, I'm just 5 to 10 minutes. I'm just explaining this. S1 of t will multiply cos omega ct. S2 of t will be sin omega ct will multiply, and summation will be takes place of this. This is exactly quadrature phase, because look back, the phases of whatever the information will be protected with this carrier wave. Okay, exactly. And information, let us say 1, S1 of t is 1, S2 of t is, let us say, representation of the 0, as we told you already in the last classes. This will be multiplied with this, what you call sin omega ct. This is absolutely quadrature phase with this, and hence we call it as a quadrature phase shift. And this will add, and we are going to send the signal from the transmitter QPSK absolutely by this equation S1 of t into cos omega ct plus S2 of t into sin omega t. Okay, exactly this. Now, as I mentioned, this is the how exactly goes the equation. What is exactly the equation of quadrature phase? We look back here. The signal of BPSK, any kind of BPSK, that is binary, we are going energy of the signal and phase and frequency information, which you are told very clearly in the second unit. Any kind of a signal, whether it's BPSK or any kind of FSK or QPSK or any signal, it should contain the energy of the signal, which is indicated by EP, and phases of the phase and frequency of the signal, that is representation of the, this is exactly the signal of QPSK and EP energy basis, and this is exactly, we told her, square root of 2 by 2 TB into cos 2 pi CT. It is the phase and information of this signal which represented any kind of a signal. It may be 1 or 0. Okay, so this is for a QPSK, what we are told, this is absolutely for BPSK. For QPSK, what we are told, we have to change into the frequencies. Okay, see, look back, frequency, we are given a word absolutely called as a quadrature. Quadrature means, that means, for example, one symbol 1 to be transmitted by 2 bits. 1 is for, that means same 1 will be for S1 up to complement of 1 will be sent to complement of 1 is equal to 0 will be sent to the S2 of t. Where exactly in BPSK we are going to send one each symbol by changing the phases of the carrier wave in a single carrier. Please mark it. Where exactly here in the QPSK we are going to transfer each symbol, okay, by 2 this thing. Taking one signal as that of the sending, let us say one first symbol, one has to be sent as per S1 t, it will be sent in as per that in S1 of t, and complement of 1, that is 0, will be sent it S of 2. Let us take some advantage, because advantage like to be get is using a bandwidth efficiently. Okay, so because you look at QPSK, we use the one carrier. Whatever the full bandwidth available in the BPSK will completely used in the one channel of the bandwidth will use for one carrier wave. Where exactly here one wave will be sent after some other wave. That means the rate of transmission rate will be increased. Okay, exactly. Probably you can understand the fact why this. Why we exactly that. Look back. So that means that QPSK will help you to improve the bandwidth, channel bandwidth. using the bandwidth utilization efficiently, where exactly one bandwidth for one channel signal in BPS. That is what big advantage for QPSK and UPSK. Right. So look back here. This is the one of the equation for S1 of t. Now let us take the QPSK equation absolutely with this equation to 2e by 2 into cos 2 pi ct. Here we have mentioned the quadrature, but the phases of the between the S1 of 2 S2 can take pi by 4, 3 by 4, 7 by 4 exactly like this. So instead of, even though we have mentioned quadrature, the phase between the S1 of 2 and S2 of 2 can be taken different value. Generally it can take the four values, pi by 4, 3 by 4, 5 by 4, because it has to maintain the quadrature. Look back, the quadrature difference between this is 90 degree. Okay, quadrature between this is equal to 90 degree, and hence the basic definition of the quadrature will be hold down. Okay, even though phase is 5 by 4, 3 by 4, because the difference between this to this and this to this and this to this 90 degree, and hence the basic principle and definition of the QPSK has been followed even that. So with this condition that we wrote the equation of the wrote the equation of BPSK into QPSK is as follows. We have written everything as same except we added 2i minus 1. I is equal to 1, 2, 3, 4, etc. Okay, this is for I. Where there is a 0, when there is no 1, when there is a phase difference is pi by 4, there's pi phase difference in the two signal, it absolutely 90 degrees less, so 0 elsewhere. See, this is exactly equation of QPSK. Very important, please mind it. You should not say why this quadrature. The quadrature difference between the pi by 4 and 3 by 4 is pi by 2. Okay, exactly. So look back here. So energy, you know what is the energy of the signal, the magnitude of the signal. What is T is a time to symbol to the frequency of the carrier frequency used for both ML. See, look at the carrier frequency is that. In the QPSK, I'm going to use a two signal, one signal for the signal to be transmitted and the complement of one exactly B to 2. I told you why the advantage is because to use the channel bandwidth efficiently, and that is what exactly when we compare with BPSK. But of course, when you consideration the QPSK, there will be other like a disadvantage hardware circuit. Let us not bother about, since we are just looking at the how the transmission takes place between the transmitter and to the receiver via channel, that is AW channel, the digital communication. Let us concentrate much. Okay, exactly. The FC, look back here. E is equal to transmitted the signal of the energy T FC. FC is equal to what exactly? The carrier frequency utilized. The carrier frequency absolutely is given by, is depends upon the look back. The carrier frequency is an integer value NC bit, where what we call as an integer equal plus or minus 1. That means for a given one frequency, there will be two kind of frequency, two kind of the plus FC and minus FC. That means phases get changed. That means possibly we will have 2 bits. Okay, exactly. So one, look back, I mentioned one for positive value and another for negative value. So that means we are this, the possible value setup. That means for one symbol, there is a 2 things. Okay, exactly, please mind it. For one symbol, there is a 2 bits. One for say, another one is complement of that. Let us say S of 2 it as per the BPSK. That is why this kind of we call graded encode set of a die bits. Die bit means for one, there is a 2, one S1 of 2 and S2 of 2 in a QPSK. So that means this is exactly we call gray coded, a gray encoded set of die bits. 2 bits for information. That is 1 bit for S1 of 2 and 2 bit for S2 of 2. I mentioned it. S1 of 2, for example, if you want to transfer the bit S1, 1, it is S of 1 to S of 2. Now let's go back, because signal space of the diagram is most important, especially when we're talking about coherent deductions at the receiver level. When this is SI is equal to 2 square root of 2 by 18 to cos 2 pi ct into 2i minus pi by 4. So look back here, the phases between the two. So QPSK, let's take the 2 equation. Exactly, it takes the only 2 equation, that is a 2 is a 2 equation signal, that is 2 signal S1 of 2 and S2 of 2, which the quadrature phase difference between them. Okay, exactly 2e by 2 into cos of 2 pi ct into I minus pi by 4. Exactly, expanding this terms, look back, a plus b, you will get back to this equation. Look back here, this is 2 equation. Next one, a minus b, this is 1. Look back here, cos 2 minus pi by 4 is a 1 equation, and sine of 2i minus 4 is another equations. So, but in generally BPSK equation is given by energy magnitude of the signal and phase of the signal. Just compare this two, comparing this two, we can say that this is a QPSK QPSK signals will have a 2 orthogonal, because sine and cosine. So these phase differences has to be a quadrature. There is a 90-degree difference. That means we know to represent this two, especially before. As we know that the signal before transmitting from the transmitter, we need to multiply the basis function to it the magnitude of the energy which is to be transmitted. Okay, this basis function will contain the frequency, phases, and time duration of the signal to be transmitted. So that is which you are going to multiply at the transmitter is at the transmit before transmitting itself. Okay, so pi 1 of 2 is equal to this equation. This will 2. When you compare this, it have a two orthogonal function cos 2 pi ct and sine 2 pi ct's. Okay, exactly. So that means we have what is exactly that there might be two message points. When you compare this, we can compare this equation. So we can say there is a two message points. One is exactly 2e. So basically what the magnitude, we are interested only magnitude. Magnitude is only depend upon the energy of the signal. That is why a signal representation will depends upon the magnitude of the energy of the signal into the phase. Okay, exactly. Phase of the signal, we square root of e into cos 2i minus pi by 4, and another one is minus 2e cos sine of 2i minus 5 by 4. That means the message points of this message points of the QPSK, which is absolutely used by the receiver in order to detect the information, is having a two message point. One message point is equal to what? Square root of e into cos 2i minus 4, the minus root e in sine of 2i minus 4 of pi by 4 this. Okay, so since I told you for one signal there is a 2 bits, that is exactly 2 bytes. So that's possible for a 2 bits, because we are getting into two signal. Each signal will have a two frequencies exactly. So 2 plus 2 is equal to 4. That means for one symbol there is a possibility of gray coded is absolutely 4 of this, pi by 4, 3 by 4, 5 by 4. This is plus what I call it as okay, plus e by 2 minus e by 2, absolutely with this consideration, all this thing. This is absolutely coded. This has to be get from last equation which I mentioned. The message point of has been done this. The M1, M2, M3. This is M1, M2, M3, M4, which is exactly plotted in the signal space. This is 5 by 2, 5 1, because it contains two phases equal to basis function. It needs a two-dimensional, and message points are is equal to what? M is equal to 4, right? So this is QPSK forms. How the QPSK form, how the detection takes place. Absolutely the receiver. That is what exactly not. How once the QPSK is formulated, that is exactly formulated as per the equation which we defined in the last pages. In the last, what will happen in the same QPSK signal will be received by the receiver. It bifurcate the signal. It bifurcate exactly the signal into what? Odd and even. This is odd and even, which is compatible with this. So when you okay, odd and even. So once it odd and even consideration, and the what I call it as, okay, binary odd and even takes place. Okay, exactly. Okay, odd and even, right? Odd and even, and summation will be takes place. That is what exactly identification in generally how the process how the design of the receiver coherent detection takes place exactly now. So when you come back to this is next is exactly generation and coherent detection. Generation takes place. Look back here. This is the generation block which I already explained everything here. See, binary. This is the input. Binary sequence of the input comes here. Polar, because as I mentioned it, when you use a phase shift key, we need of the polar NRZ level. Is this polar NRZ level? Absolutely, with this exactly polar NRZ. Okay, exactly consideration with this equation, which is which is a basic principle used in basic line code. You absolutely used in PSK. This is that is why you use the polar NRZ container. Once it goes, it deducts the phases of the two things. Okay, exactly phases. Demultiplexers detect the phases of a different, because two signals will come absolutely as for the QPSK, S1 of 2, S2 of 2, which is absolutely quadruple phase difference between this. This demultiplier detect the phases of the two signals. One is exactly called phi 1 2 and phi 2, and sorry, A1 of 2 and A2, and this will be multiplied absolutely by basis function, because the basis function is most important, as I mentioned, which will identify the phase and frequency of the signal, which is also a multiplied to the signal. That's one of the there is energy of the magnitude of this, that will convey the message before transmitting at the receiver, and this will be multiplied with this help of QPSK signal will be identified by the decision. Okay, exactly. This is exactly the QPSK transmitter. Okay, this demultiplexer identify the 1 and zeros. Okay, exactly. Demultiplexer and the QPSK transmitter will identify we'll identify the 1 and zeros and split according to the P1 of Y1 of 2 is get multiplied and QPSK signal to be transmitted, absolutely generated. When you come back to the coherent deduction, how this receiver signal goes, this is as absolutely simple, and received signal x of t is equal to pi 1 of t, pi 2, and multiplied by, as yesterday class I mentioned, pi 1 2 will multiply integral of this decoder decision. This is, and the decision device, okay, exactly decision device will compare the voltage of this threshold voltage. When you compare with this threshold, if this is more than this, then it predicate chosen 1 is the value high greater than, that is 1, because threshold of the maximum voltage divided by the threshold voltage, this decision divisor is 0 voltage. Exactly, this is x of 2. X of 2, this is the input has come, which will compare the output voltage of the threshold voltage. X of 2, compare this. If this is a voltage less than this, what will happen? Absolutely, it becomes, this is less than this. It understands that because the maximum voltage can be hold by the decision device less than 1 is less than 0, will estimate. That means depending upon the what kind of what kind of the input will come, the decision devices will conclude whether the transmitted message is 1 or transmitted message is 0 by looking the taking threshold of this, okay, which I mentioned already. This is absolutely correlators, and already I mentioned it. Now let's go back. Error probability of the QPSK. This is the equation which I mentioned. This is the absolute equation, square root of 2e by t to cos of 2 pi ct. What is error of probability? Please mind it. Error of probability of the receiver is the one identification or a deduction of the transmitted message at the receiver is false. That means if the transmitted message is 1, okay, and the identifier, the deducting of the same information, the receiver is 0. That is exactly called as error of probability. For a successful communication, for a successful BPSK or QPSK, any kind of a system of communication, you should have error of probability as less as possible. Definitely, it cannot be a make a 0, because this system cannot be free from what you call it as free from complexity. For it is not an ideal case as of today. So this is the equation, as you know, just expanding this. But please remember, we are talking about AWG channel. Until unless otherwise I mentioned in the next anything, the channel, the transmitted channel through which you are going to transmit the message and transmit it to the receiver, which is exactly called as AWG, additive wide Gaussian channel. Okay, so the output of this is equal to what? S1 of t plus WT. The S1 of t is equal to the information to be sent, and it is to be multiplied the basis function before sending a cross from transmitter to transmit to the receiver through a W channel. And when you say AW channel, there is a noise present, what we call as a white noise Gaussian. Why? What we call white Gaussian noises? The noise is constant; it does not vary. So, look back. This is, see this when you say the but output. As we know that how the coherent deduction will be, as soon as the input is received by the receiver, it will multiply with the basis function. The basis function will contain the information about the phase and the frequency of the signal. So we should equate whatever the output of this into there are two signal, x1 of 2, x1 is equal to for s1 of t, x2 of 2 is equal to what? s2 of t, which x1 of 2 and x2 of 2 received input at the receiver signal. So x1 has to be with the phase of what? Exactly as per the equation, cos 2 pi by 4, and this equation has to be multiplied with cos 2 pi by 4. But you know, this is output signal at the receiver. That means the signal is transmitted from the QPSK via channel. There is a kind of a noise, what we mentioned with the white Gaussian noise has been present, and this is to be added together. So that's why I added W2, and I'll get back. So when you take for this, when you just rearranging all these things, x1 is equal to plus or minus square root of e by 2 into Wn. X2 of this is absolutely what I told you, this QPSK. The first is exactly we call as in-phase path, and the second is exactly was quadrature path. Similarly, there is a quadrature output is equal to x of 2 this, okay, exactly x2 of this, okay. So that means signal energy bit is equal to e by 2, okay, exactly. Signal energy with the noise spectral density equal to, well, just looking back the two equation, x1 of 2, x2 of 3, x1 of 2 is directly proportional to square root of v. Please mind it, the probability error will be decreased because x1 is directly proportional to, let us say, e is equal to 2, e is equal to 16, e is equal to 4, 4 square is equal to 16. That means square root of the 16 is equal to 4. That means as you increase the energy, the magnitude of the signal, the probability of error will come to a less, as because of x1 of t is directly proportional to square root of a simple, please mind it, square root of 4 is equal to 2. That means as you increase the energy, the probability energy will also decrease. That is what exactly consideration. How do you increase the energy magnitude of the signal? Are simple. Just make the apart, because let us say 100, the information you are going to from transmit to the receiver through via the AWE channel, just make apart 0 between 1, a part of that. So this is, see, look, very important, how you're going to calculate the basic principle absolutely involved in the QPSK. The probability error of reduction is done, because QPSK system, the two channels will be there. One for one symbol to be transmitted 2 bits. Okay, exactly. So one channel we call it in phase and out phase. That means two kind of a BPSK has been added together at the output level. Exactly. So that means if I take the probability error of 1 BPSK of in phase, probability error for the in quadrature phase, absolutely I'll get back to P is equal to 1. I can get that the probability error of the QPSK. Now let's take, as we know that, what is the probability error of the probability error of a PPSK in phase path is given by of this. In a similarly in a quadrature path is also a same path of this, that is P. As you know, BPSK probability error we have found it P is equal to Q into square root of 2B into N naught, and similarly PPSK Q into what exactly? Square root of E by N naught. Okay, so that from working of this, okay, so that means when you take that, this is absolutely for one part, this is for in phase path, this is for what exactly? Quadrature path. So when you add together, you will get back to the QPSK. But the probability is not happening is this. Probability is happening is absolutely by taking, let's take one part as the in phase path. This probability is happening by probability statistics theory. You know the probability is happening is 1 minus the probability is not happening. Okay, right. So when you just mention it, the P, this is probability, P is mentioned the what? Probability is not happening. 1 minus P is equal to 1 minus Q into square root of E by N square. Okay, just take this is A minus B whole square formula, and just this thing the average by ignoring this for a signal. This is exactly for probability is happening for one part, that is now probability happening for what exactly for both the signal for both we'll get back to 1 minus PC is equal to what Q into square root of this. Okay, so by since quadrature term, as you know, it mentions the it mentions the only a what you call it as only a noise product. That's what we call it as IP, that is intermodulation product, which an absolutely can remember P is equal to 2Q into E by T. Okay, exactly. So that means, see, look back here, the probability when the transmitted energy, okay, exactly, look here, there's note that there are 2 bits per symbol in the QPSK. That one bit is for one phase path and another bit for quadrature. So that means E is equal to 2B, P is equal to 2Q square root of 2B into N naught. So what is exactly the bit error rate? How many bits by over time it's called as how many bits you are going to transmit it in over a time of this, that is exactly number of bits by number of time taken to transmit, we call as a bit rate. We shortly termed as exactly called as B or bit error rate. Must be one off of the average probability error in terms of EB by naught for a QPSK. Okay, since 2 bits of the per symbol or in the QPSK, absolutely that means 2 symbol will go into for sending one signal, that is average probability error in terms of this by 2. Okay, we'll get back. This is exactly called as bit error of QPSK is equal to Q into square root of 2B into N naught. Okay, exactly. So this is what exactly. So that means you are getting this already. I'll expand. Okay. So why QPSK system? Because it uses very important. I mentioned it. The QPSK system performance better than the BPSK due to QPSK uses channel bandwidth better than the binary PSK. We approved it here. Look, the bandwidth 2K instead of 2Q. As of in PSK, we have only Q in QPSK for a P. That is a symbol of error. Absolutely can mention. We can conclude an interface that the QPSK system performance for better than the PSK due to QPSK uses channel bandwidth is better than the binary PSK. That is why the QPSK system preferred over BPSK system. Now exactly the power spectrum with QPSK, which I already explained everything. It's a simple for the notes. What is exactly the power spectral density? The power spectral density is contained the information about the signal, the information transmitted. Here we used only one carrier wave, but two different spaces within a different signal. So that means one carrier wave, that is the frequency of the signal is a constant, but only the phases of the current. We please manage an angle modulation, the frequency is remain constant and phase will be changed, or phase will be constant, frequency changes another type of modulation which we have talked about in the initial introduction of this class, this chapter, what we call it as a frequency shift K. Okay, exactly of that. So that means here the QPSK, we are going to use a one signal with a one frequency signal. Absolutely, here we are going to be what we got. We are. We are all the information absolutely protected in this part of this. Okay, exactly. So that means QPSK, that is probability density function, not a probability, sorry, but the power density, spectral density, absolutely concentrate over exactly the plus or minus, because plus or the carrier frequency, only one carrier frequency, and the use equation is absolutely given without any derivation. C S of BF is equal to 2 into sine squared C into TF of this. Okay, exactly. So this is, now let's come back to what is exactly the M array PSK. Look back here, the very important, this is the QPSK equation. QPSK equation is what exactly? We are going to send two signals for one symbol to be transmitted in a 1-2 path. So exactly in phase and out phase, these two will be absolutely summation together to identify the QPSK. Better advantage is to use the channel FE effectively, because we have proved it in the last section. Okay, here what will happen in MRF PSK, instead of the pi by 4, we are defined only for a quadrature. It may take pi by 4, 3 pi by 4, 5 by 4, 5 pi by 4, or 7 pi by 4. But instead of that, difference of that, I'm going to use what you call, instead of m possible values, I'm just removing one of the condition was the quadrature. So that means what exactly? The quadrature piece, that is now a certain, or otherwise I can say that is MPSK is another specification of the quadrature, where exactly the quadrature specific condition has to be met exactly here. So the specific condition absolutely specific condition has to be met here, exactly that is good. Two signals S1 of 2, S2 of 2 should be a 90-degree difference between that, but instead of that here I'm going to use M. So that means this pi by 4 will absolutely change by M. So look back, this is exactly called as the MPSK. That means there are the possible, instead of taking the quadrature phase between, there are possible of taking what exactly, there are a possible taking M possible of the phase, such kind of the PSK we call as M array PSK, very simple, which are automated. Okay, the signal, okay, exactly. Therefore, signals of MSK is a two-dimensional, because look back here, absolutely signal space of memory PSK, it has to be so many signal of PSK. So two basis function is required. Two basis function is absolutely required. Phi 1 of 2, pi 2 of 2, exactly here. Phi 1 of 2, pi 1 of 2. Then you take the possible value of m's. So if you take the n value, okay, if you take the n value, two-dimensional, n is equal to 2, m is equal to 1, that means m is equal to 4, that means possible is m is equal to 16. So n is equal to 2 means 2 equate 2, that is 5 by 2 and 5 by 1. The message is called m4, m1 of this. Okay, exactly. m1, m2, m3, m4, and all these messages. And I marked here, very important here, in order to distinguish between the two messages to be transmitted. That means when you pass the message between the transmitter to receiver and our mobile communication, or any part of that, or in a communication purpose of that, what will happen? There must be something decision boundary. Decision boundaries absolutely indicate what is the influence area of the particular messages. So look back here, and either side of this indicated here. Okay, exactly. So this means what is exactly the probability error of this? See, probability error of the QPSK multiplied with the distance between the two message is absolutely the probability error of symbol of MPSK. Yeah, as simple as the working and principles are quite same, but only thing is we are sending the messages in a different phase as rather than the quadrature phase what we have mentioned in the QPSK. So that means error of probability of the MPSK is equal to error of probability of the QPSK, or error of the probability of QPSK into LCD, the distance between. Look back here, this is exactly the LCD distance between the two messages, exactly in this. So that will give the probability. Deducting probability of error symbol is deducting the information at the fault. That means whatever the message is for information is passed is 1, deducting the information absolutely what this one. So when you multiply this into the LCDN with the help of the QPSK, we'll get back the probability error of is equal to probability error of MK is equal to 2K into the square root of 2 by N2 into sine of pi by b. This is absolutely the distance. There is no, this has been defined. there is no derivation for this. Okay, exactly. When come back to the power spectrum of M array, so T is equal to data, T is equal to TP by 2 p.m. the simple duration. So okay, okay, exactly. The spectral array is same as equal to what? So spectral array indicates the maximum, what you call it, indicates the magnitude of the power of the, that is energy, that is information absolutely present in this equation in the spectral diagram with a carrier plus or minus. That means is a wire, the spectral density of the QPK, spectral density of the M array PSK as same as the what, as same as the QPSK, but it takes the different values M. So for a different values of M are absolutely defined here, and the value, exactly the value of the what is this is given by this equation. Just it is a just derivation, and this is distance between the 2 points of this. Okay, exactly. So now the bit array, by considering what a B is equal to 2 by T, the bit array rate of the, this is a simple equation they derived it. And similarly the bit array in terms of the bandwidth of the bit array is given by this equation log 2 by, from this is if bandwidth efficiency increase as a number of we also M freezes, as more passing of the signal, that means M array PSK will help you out to improve the efficiency, because same signal full of the channel bandwidth utilized by off, we are sending the off channel bit with the signals one strings of zeros, so that and whatever the bandwidth will be utilized in off way. Okay, exactly. So this comes conclusion of the M array PSK. Okay, exactly. Tomorrow we can go for M quadrature amplitude multiplication is quite easy and as simple as that. If you could understand the PSK and MPSK and this quadrature is quite easy, we'll complete, then we can go for what you call FPSK is quite as simple. Okay, so simple, and the next class will be announced in the next class. Okay, very shortly. Thank you.